Problem number 5 wants you to take this piece of a sinusoidal curve and from it write an equation. On the left here, I've drawn a small sinusoidal equation, and you'll notice I cut it in half. What I wanted to point out with this is the part that's on the top and the part that's on the bottom, right, just to the left of the divide and to the right of the divide, are actually mirror images of each other. They are reflections across the x-axis. When you cut a sinusoidal curve in half, what you get is enough information to go ahead and finish the curve. Not only that, but you can cut the curve into quarters. You've got 1, 2, 3, 4 pieces, and each one of those pieces is actually a transformation of the other. 1 and 2 are a reflection across the vertical line there. 2 and 3 are a rotation of each other, 180-degree rotation symmetry. And then 4 and 3 are also reflections. Really, you only need a quarter of the entire sinusoidal period in order to be able to figure out what it is you have and write an equation for it. So let's go back to our problem. First thing I want to do is put some information in here. I want to mark the top and the bottom. Those are the blue lines, because those are going to be the upper and the lower bounds. And I want to mark the midline. In this case, it's 0.5. And you do that by counting how many spaces there are between the upper and lower bound, cutting it in half, and finding where that is. In the next diagram, I've done a few things. I've put some numbers in on the theta axis. I've also marked the amplitude, which is the distance from the midline to the upper bound and from the midline to the lower bound. And I've added a bit to the curve in order to give us a better picture of what it's supposed to look like. It's easier to figure out here what cosine equation you can write for this because we know where the curve hits the maximum. If you look at where it hits the midline, there's no marking there for degree measurements, so we would have to guess. But there's no guessing for the maximum there at 200. We know that's where it hits. How do we know? Well, we know it hits at 600, and we know that it hits the bottom at 400, and we know this is the halfway mark, so the other half also has to be 200 degrees wide, so we know it hits at 200, which means that there's a 200-degree shift to the right for a cosine curve. The standard form of the equation here is y is equal to d plus a cosine b theta minus c. And each of those letters relates to the numbers we've already got up here on the screen. For example, the 0.5 is the midline, and that's the d in the equation. So we substitute that there. So we have y is equal to 0.5 plus, we know that the coefficient of cosine is the amplitude, and we know the amplitude is 3.5. So we've put the 3.5 in for the amplitude. We've replaced a with 3.5, and we know that the horizontal shift, the phase shift, is a positive 200 degrees. So we put that in where c is. Now we have almost the entire equation. I left b to the end because that's what some people find the most complicated. B is equal to 360 degrees divided by the period. So the period is 400 degrees, and the way we know that is that from 400 degrees to 600 degrees is 200 degrees, and that's half the graph of one cycle. So if we double it to get the other half, we know that the period is going to be 400 degrees. That means 360 degrees divided by 400, that reduces to 9 over 10. And if we put 9 over 10 in, we have the equation. Y is equal to 0.5 plus 3.5 cosine 9/10 times theta minus 200. I'm usually not satisfied for myself that I've got the right equation. If I can, I always go check it somewhere on a grapher. And if you look at it, I've got the equation there on the left, and the graph looks pretty much the same. The maximum is 4, The minimum is -3. At 400, the graph hits the minimum. At 600, it hits the maximum. That fits. That's the equation we were looking for.